All right, we've talked about inverse trigonometric functions, and hopefully we have a better understanding of domain and range of these inverse trig functions. Now let's talk a little bit about the composition of trig functions using inverses. So go back and remember to chapter 1, where we talked about inverse trig functions for the first time in this course, and we said that if a function and f inverse are inverse functions, then the following statement is true. We would say that f composed of its inverse is equal to x. And then also its inverse composed of the function itself also has to be equal to x. And this is just one way of reminding us that inverse functions undo the operations of the other. So for example, if one function were equal to 3x and its inverse were, if its inverse function were equal to dividing by 3, if I were to say f composed of its inverse function, this is one way of saying 3 composed of its inverse function, which is x over 3. Well, this function is dividing by 3, but then you're multiplying by 3, and so what it's doing is it's undoing the operation of that function. That's equal to x. So inverse functions work as undoing the operations of the other. Well, how does that relate with inverse trig functions? So let me just get this out of the way. Well, this leads us to being able to identify a couple of inverse trigonometric function properties. That is to say, we can say that sine composed of its inverse should give you x, and the inverse sine or arcsine function composed of sine, y, should give you y. If we can say that the following statements are true, that is to say, if we're saying sine composed of its inverse function or arcsine, remember that the domain of arcsine, right? The domain of arcsine are actually going to be ratios, right? X here is a ratio. If that is between -1 and 1, then we can just say that this entire composition should just result in x. And the same deal when we're talking about arcsine composed of sine of y. Remember that the input of sine, what we're plugging into a sine function, is an angle. If that angle is within the restricted domain of sine, with the restricted domain of sine such that we are able to have an inverse trig function, then the arcsine composed of sine is very just simply y. There's really no evaluating that we need to do. We can just use these properties to evaluate these compositions. Now, do we have to know these properties? And the answer is no. You can do all of the problems below without memorizing any of these properties, really. But they do make our lives a lot easier. So the bottom line with these properties here is just know that if the domain of your inner composition function, is within the restricted domain or range of these inverse trig functions, then it's simply going to be equal to whatever it is your argument is. Okay? So let's look at a few examples, and let me actually start with something like let me actually write something out before we try some of these problems below. Let's do something like arcsine composed of the sine of 3 pi over 2. Okay, so something like this. Now, first off, ask yourself, is 3 pi over 2 in the restricted domain? Is it in the restricted domain of sine such that it has an inverse function? So look at 3 pi over 2 and look at the restricted domain of sine. Is 3 pi over 2 in that interval? And the answer is no, it is not. And all that means right now is that this inverse trig property doesn't apply. That is not to say that we can't evaluate this composition, right? So we can't just easily say that it is going to be equal to 3 pi over 2. We can't just say that this is 3 pi over 2. Had this angle been in this interval, then we could just say it's whatever this argument is. But this is still something that we can evaluate. Because ask yourself, what is the sine of 3 pi over 2? And this is equal to -1. So what is the arcsine of -1? The sine of what angle gives you -1? And the answer is either -pi over 2 or 3 pi over 2. But because we're evaluating an inverse trig function, we would say just -pi over 2. That is an angle that is within our restricted domain of arc sine, or sine, so that we could have an inverse trig function, okay? So let's try some other ones. All right, let's try number 1 over here. Well, ask ourselves. Let's look at tangent composed of arctangent of -14. So you might be tempted to ask yourself, okay, the tangent of what angle gives you -14? And the answer is, I don't know. And I really don't. Off the top of my head, I actually don't know the tangent of what angle gives me -14 as an output. But that's not really the point of this question. The point is to look at this argument here. Look at -14. Is that within the domain of our inverse trig function, our inverse tangent, our arctangent here? Look at where x is. Well, x can be all real numbers. Oh, well, so that the answer is yes, it is within the domain of arctangent. And if that is the case, the tangent composed of the arctangent of -14, this is simply going to be whatever this argument is. So it is -14. Okay. What about something like number 2? Number 2 here. Look at pi. Let me highlight pi. Is that within the restricted domain of sine such that we do have an inverse trig function or inverse sine function? And the answer is no. Pi is outside of this domain right over here. So we can't just say that it's pi like we did in the previous problem. We can't just jump to saying that it is whatever that argument is. So we got to actually try to evaluate arc sine of pi. And actually, well, think about that for a second. The arc sine of pi, that's kind of like asking ourselves the sine of what angle gives me pi as an output. And this is what should cause you to pause. What is the output? What is the range of sine? It's strictly from -1 to 1. Pi, it's outside of that range. So there is no angle that when I take the sine of that angle that I would get something ever greater than 1. So this here, there is no angle, so this is going to be undefined, right? Pi is not in the interval from -1 to +1, okay? All right, what about something like number 3? 3 pi over 2. Is that within the domain of cosine such that we have an inverse trig function? So looking back here, look at where y is, right? Look where y is here. Can I basically, not to ask, can I evaluate this, but actually more, can I apply the property? And the answer is no. 3 pi over 2 is greater than pi, so I will be unable to use this inverse trig function property. Now, however, can I still evaluate this? Well, I think so. Cosine of 3 pi over 2 is going to be equal to 0. So like, while I can't use the property, it does look like I can still evaluate this. What is the arc cosine of 0? That is to say, the cosine of what angle gives me 0? So let me actually write it this way. Cosine of what angle gives me 0 such that I am in the proper range of arc cosine, and that would be pi over 2. Okay, let's do one more together before you try a few on your own. All right, now arc cosine of 1/2. Well, the arc cosine of 1/2, can I apply the property here? And the answer is no, I can't apply the property because this is actually not a composition consisted of a function and its inverse. Sine and arc cosine are not inverses of each other. So the property does not apply here. But can I still evaluate this? What is the arc cosine of 1/2? Well, this would be pi over 3. So what is the sine of pi over 3? This would just be equal to √3 over 2. Okay? Go ahead and pause the video and try numbers 5 and 6 on your own. Hopefully, after you've had a chance to work on this, you should see that I can't apply the property because this is not a composition that is composed of its inverses. But I've got cosine composed of arctangent. This would be -pi over 3. So the cosine of -pi over 3 is equal to 1/2. Arc cosine for number 6. Arc cosine composed of, there's a little bit of a typo there. I should have a parentheses around there. I apologize about that. Arc cosine composed of sine of -pi over 6. This is equivalent to the arc cosine of -1/2. And this should give you 2 pi over 3. Okay. All right, let's try some other problems now involving inverse trig functions and their compositions. For number 7 here, let's go ahead and let's actually draw a triangle to find the exact value of this. Because if you're sitting here looking at arctangent of -3/4, you might be tempted to ask yourself, okay, what angle, when I evaluate the tangent of it, would give me -3/4? And this is not a ratio that I am accustomed to getting out of any angle within our unit circle. So instead, I'm going to actually draw a triangle here. So how could I draw a triangle that would represent -3/4? And by looking at the way I've drawn my triangle right now, I'm already off to a pretty bad start. Because I see that the tangent of my angle is going to give me a negative output. And where is tangent negative? Tangent is negative, so I'm going to have to delete this. Tangent is negative in quadrant 2 and quadrant 4. Now, think about arctangent. Arctangent deals with angles in which quadrant? Between quadrants 1 and quadrants 4. So I actually can't be looking at the angle in quadrant 2. It has to be the angle in quadrant 4. That's where tangent is negative, and that's where all of the angles for arctangent result in quadrants 1 and 4. So now that I see that we're in quadrant 4, we're going to say that the outputs, I know that when I take the tangent of my angle theta, opposite over adjacent is -3/4. So this would have to be -3, and this would have to be +4. And hopefully you recognize here that this is a Pythagorean triple. So that means my hypotenuse here has to be 5. So do I know my angle? I don't know my angle, but I have all 3 sides. Now I have anything that is necessary to evaluate this. So I can say the following. I know that the arctangent of -3/4 gives me some angle theta. I can then say that the cosine of this same angle theta is going to be adjacent over hypotenuse, which is 4/5. So that would be my output here. Okay. All right. What about something like number 8 over here? Okay. So looking at something like this, well, the arc sine of 2x, this definitely, I don't know the angle for it because I have a variable in my domain of arc sine. So all I know right now is that this results in some angle sine. The arc sine of 2x is, or this results in some angle theta, I should say. So the arc sine of 2x is going to give me some angle theta. Oops, that's a terrible axis. And I know that sine is positive in quadrants 1 and 2. So it could initially be here in quadrant 1 or quadrant 2. However, I should probably make that more symmetric. However, I know that the outputs of arc sine have to be in quadrants 1 and 4. So I can't actually include quadrant 2. So I know that my angle theta has to be in quadrant 1. Sine is opposite over hypotenuse. So 2x over 1 would be my set tentative ratio. And I can use the Pythagorean theorem now to figure out this value here. Let's just let a be equal to this side. Okay, be equal to this. So I can say 2x squared plus a squared is equal to 1 squared. A squared then is equal to 1, oops, that's not clean notation there, minus 4x squared. 2x squared is 4x squared. A is equal to plus or minus root 1 minus 4x squared. And since I'm only dealing with angles in quadrant 1, I know that my a value has to be positive. Okay, so now that I know this adjacent side here, I can then say the tangent of this angle theta here is equal to opposite over adjacent, which is 2x opposite over my adjacent side, which is root 1 minus 4x squared. And we should rationalize this. We can say that this is 2x times root 1 minus 4x squared all over 1 minus 4x squared. And there it is rationalized. Okay. All right, let me just do one more type of problem with you all. Let's try something like this here. Use an inverse function to write theta, which represents this angle in case that wasn't clear, as a function of x. Well, which 2 sides are we given? We are given our adjacent side and our hypotenuse. So it would make the most sense to use which trig function. and cosine would be correct. Cosine of theta would be equal to 4 over x. Well, how do I rewrite this so that theta is a function of x? Well, I would then want to say theta is equal to what? It is equal to the arc cosine of 4 over x. Theta is defined as being the inverse cosine function of 4 over x. Remember, this is another way of asking the cosine of what angle in our restricted domain results in 4 over x. Okay? All right. Well, hopefully this gives you a good sense of how to work with compositions of inverse trig functions. And you'll see that over and over, time and time again, one of the most important things is to think about the restricted domain of our inverse trig functions and therefore its restricted range.